So usually every year I give a state of RTEMS. Last year I gave where SMP was headed, and I've wanted to do this talk for a while. RTEMS has two facets. One, it's a very old project. It's 25 years old this year, and we have outlived 3 bug tracking systems. We're on our 3rd wiki, our 3rd or 4th website. So we don't get to put a VAX in cryogenic suspension. We just have to suffer through tool replacement and learning new things and going. So if you have trouble from a community management and building projects and living projects, the other part of ecosystem is we're trying to learn more and hopefully get more feedback from the community so we actually serve your needs better. So some of these are guesses on our side that we think are the right things to do based on our experience on applications. But the ecosystem has two sides. Part of it is what's used to run the project, and part of it is the support tools for RTEMS that you use but you don't think about because we never talk about them. We talk about runtimes and multiprocessing and all those kind of things. So one of our keywords recently has been reproducibility. We want to take open source, being an open source RTOS, and turn it into an advantage. So we're going to deliver source. The goal is to be able to have a complete online database of test results against known reference platforms, including something close to pretty much everything you're using. The Sparks in particular will have references to go with. The other part of that is that you will eventually be able to reproduce all test results on your own. You can do that now, but you'll have a reference database, including GCC and all tools. And we will deliver everything to you as source and easy to integrate into configuration management. The other side of this is that we've got a framework that's a collection of tools, and it is really an ongoing and active effort. And it's been sponsored some's been sponsored by NASA, some has happened a lot by student, and some has just happened by sheer will if somebody sees a need and does a prototype. The first thing that happened started out actually from MMS finally was the one that gave us the clue. You guys added a patch to the C library to build it that gave you like 5 or 10% more bandwidth on your limited cold fires. And we realized that no matter how often we delivered tool binaries, there was a good case for somebody like you to do something really simple and boost your performance. So we said, okay, that's what we need to do. So this is where the idea of the RTEMS source builder and the RTEMS tester came from. These are actually, if you've noticed, been on the RTEMS list lately, now everybody is building the tools from source. I've seen people use everything from Raspberry Pis to oddball Linux distributions and build RTEMS cross environments. The cool thing is it fetches patches as needed, source from wherever. You can apply local patches, you get MD5 checksums, and eventually you'll get full test results if you want them for things built locally. It's very easy, very quick to use. The other side of that is something called the RTEMS tester, which uses the GDB machine interface. There's some slides coming up. And it can drive simulators or real hardware. We've got it running on the ARM Zinc and a number of simulators, and we can automate testing completely. The goal of this is, for quick developmental testing, and we're going to have continuous integration testing. So that, again, we're going to publish results. So you got to think about what we really want to deliver to you. We want to deliver the development tools, the RTOS, the simulator, so whatever you need. If it's a QEMU, we actually are now also considering those as support tools and trying to manage those and provide standard ways of building it. We're trying to move from folklore and how-to into recipes and package building, so everything is built and everything's under source code control. Our patches, we've reworked our process for managing our packages, and most of the time we don't have any patches against reasonably recent releases of the tools. And we are shipping latest versions of just about every tool. The other part of this is something that, I'll admit we've been pretty weak on. RTEMS, a lot of packages has been ported to RTEMS, but mostly you had to read how-tos on how to build them. We are now adding something comparable to what BSD calls the ports, which is also part of the RSB. So you can just say, I want libjpeg on my target, and it'll just fetch it and build it optimized for your target. So all of these how-tos are now captured in what we call recipes on how to build. And the goal is to have all of the test reports, configuration, built, tested, patches, everything's under source code control for you. So this is helping us and helping you. So we can manage building easier, capture the instructions, the patches, and it makes it very explicit when somebody's got a patch for something locally, so we can work with the other communities. And we are about half of the core RTEMS developers actually have GCC and bin utils write permission. So I mean, we actually are very active in other projects. We interface a lot with different projects that you'd be surprised to. The other part of ecosystem is, where's it hosted? What do you do? What do we do for source code control? Where are the machines? What do we do to test? I mean, there's a whole part of this supporting ecosystem. RTEMS has been a Google Summer of Code project for 8 years. We've done 3 years of the high school program Google Code In. Google has donated money to the RTEMS project, and since we didn't have anything, we wanted to have stuff to show for it, we've saved it, and we bought a half rack of new hardware. We went in together with the Network Time Foundation and the BillBot project. So RTEMS has moved recently, like if you've seen broken URLs, this is why. We're now on the 1 hop or 2 hops off the Internet 2 backbone at Oregon State. It is an incredibly fast set of hardware. We have gone from a multi-purpose machine, a multi-purpose single IP on a single host, to BSD jails with multiple IP addresses per service, so the security's higher. But it did cause some old URLs to break. We have gone from Bugzilla and MediaWiki to Track, and there has been a tremendous amount of housekeeping to kill old problem reports and try to get to the point where we can use Track to do our release countdown, and then we'll generate release reports from it. It is already integrated with, when you close a Track ticket, it already sends an email to the mailing list, to the version control mailing list. It updates GitHub, and it posts a message on IRC. So we're really, really trying to get this whole loop closed. So obviously we need more machines if we're going to build more. One of the things that keeps people want is a Mac, some kind of Mac somewhere so it can be in the continuous integration testing. And you can obviously never have enough RAM and storage. I mean, one of the machines has got 24 cores, and it still takes a while to build the tools and test everything. There are 18 target architectures and 187 board support packages in the current source, which includes every space-hardened processor, a lot of simulators, and a lot of real hardware. The other part of this is, like I said, you can't put a VAX in a corner with this kind of project that's alive. So we, with our new infrastructure, are having new capabilities. The next step after all of this is we will be eventually installing a web-based patch review system, and the goal is that the patch will be tested to some extent before a human even knows it's there, so you don't review things that are broken. There's no point. Everything a computer can check, a human shouldn't check. It's a waste of human time. And then what we want to do is, once something's committed, there'll be a standard sweep of tests that are done automatically, and then probably a regular schedule of automated tests on real hardware with a public database. And there's starting to be an effort, which is pretty far along actually, to put the user documentation into a modern format that looks into a modern tool, not tech info, so people will actually be willing to edit the documentation instead of sending me paragraphs or sentences to change. So this will enable a lot, the documentation is going to look a lot better when this is done. There's a huge effort, which unfortunately I did a lot during Thanksgiving, to review the content in the wiki to find out what's up to date, what's out of date, what's mislinked, and that's going on. So if you find things broken or anything else that's out of date or needs rewriting, just let us know. This is a huge effort. So a lot of this falls under what we call the tools project. And the base level, all of this is in Python, so we're replacing a lot of shell code with Python. That's another big step forward for us. So we're actually moving into the late 1990s or something, I guess, we're really modernizing it. It's making it more attractive for students. It makes a lot of things easier. At the bottom level here, there's a set of class helpers, like to do elf and dwarf management, symbol table management. This is called the RTEMS application package, which is important because one of the things up here is RTEMS LD, which is a dynamic loader. We've talked, some of you probably heard about it. This allows you to actually do dynamic loading of code on an RTEMS target. I've talked about the RTEMS source builder, the tester. The RTEMS LD, so is the dynamic loader. There's a host side and a target side. The target side was actually designed to be very light on hardware, and we used the MMS as a model of a typical embedded space system, because I think you're like 20, 25 megahertz and a couple of megabytes of RAM. It's pretty modest. And if you can't run in that, then you can't run in space. The next thing across the list is the RTEMS trace linker, and this was a brilliant idea by one of the old RTEMS developers, or long-standing. This is a set of tools that reads ELF, reads function signatures, and based on a pattern you define in a pattern file, will write wrapper that you've defined for function calls. And so you can insert logging of entry and exit of function calls of any type of tracing you want, and it can be automatically generated. It does not affect compiled code. It's inserted in at link time. It's something that the GNU linker does to insert wrapper functions. So that's the host side of getting instrumentation into an executable, and that technically is not RTEMS specific. It's just owned by the RTEMS project. The capture and trace engine is what is on the target side to log and trace events. So I've got some slides from that. And then we're continuing to put finer granularity and improve our coverage, and mostly coverage reporting. Our coverage testing has always been very good. 410 was near 100%. So I think I talked to this slide without even having it up. The important thing is we want to be host independent, and we want you to build from source, and we want you to have the source for the tools so you can reproduce it when you want to. And when you want to, maybe 10 years after you downloaded it. So we want it to have a clean handoff from initially when you acquire it. You have confidence that it is reproducible, it is good, and that if you have to do something to it, you can. So this is taking open source, making it configuration manageable, and giving you high ability on it. This is the entire sequence to build a Spark tool set. The first thing you do is you clone the repository, which should be very fast. You run a script which checks the host environment to make sure you've got everything you're supposed to have installed. At the moment, it doesn't check for, you can be missing some development libraries, but all the source things like having the right, like if you need Bison or Yak or something, it'll check for that. And then the last thing is, once you are inside the source builder, you do this command about 17 minutes. On a very modest, like 2.5 gigahertz, 5-year-old quad-core machine, you've got a set of tools. I think the testing, if I remember how long it takes to test GCC on that, it's about an hour on a simulator on that type of hardware. The RTEMS tester is the next part of this, and it is another part of the Python framework. It uses the GDB machine interface, which means it can be plugged into very easily. You can use simulators. If you're testing with simulators, it will run in parallel up to the number of cores on the machine, which greatly, greatly cuts down on the test time. So what we're trying to do is get to the point we can actually run build 187 BSPs and test as many of them as often as possible. Because this is the challenge. The next is just an example of how to execute the test suite. It's about 500 tests. Same really old machine, took about 10 minutes, 11 minutes. The problem we have here is, we need to reduce the runtime of our longest running tests because that puts a limit on what the timeout has to be. I actually noticed that it doesn't drive tests which need input. It doesn't detect them and they don't time out properly. There's some RTEMS for interactive tests. There's an automatic startup that on real hardware will exit, and it confuses the tester right now. We need to calibrate because some of the simulators are exceedingly slow. There's a test of the SHA hash code on RTEMS that takes like 30 seconds on real hardware, and I think on one of the Spark simulators it takes like 12 minutes. So you have to scale the time of the test timeout to the speed of the simulator, and that's something we're noticing. We want to be able to parallelize and run the GCC test suite as frequently as possible. You guys do that a lot too. I mean, and the compile farm does that. So all of the RTEMS targets are built regularly as part of the GCC compile farm, and the results are published in the standard GCC results. But what we're wanting to do is keep our database so it can be compared and you can compare to it. The coverage testing, we've been working on this very high for about 5 years, and actually we used Coverture on the right, which was an Ada Core ESA project for some of the targets. The test coverage itself is in really good shape. It's like near 100% for the core code. Fluctuates based on the daily development, and it's we do it at the instruction level. We count branches as taken and not taken, and we're at about 97% of every branch being both taken and not taken exercise for the core. But the problem is the way it's reported is basically core and lump of all. And lump of all is not good. We'd like it to be reported by like file system. So you can say that the DOS file system has this coverage, or JFFS has this coverage. So you can add something new and be able to analyze it. So because that's what we've seen. You add a new capability and the coverage is low, and it negatively impacts and gets lost in the data for the developmental. So this new version was done by an ESA Summer of Code and Space student. It's in Python. It needs some work to get integrated, but it does what it's supposed to do. It's just not ready to be integrated. So this will be a big improvement because we'll be able to tell by directory what the coverage inside a directory is, which will help us to track our progress on that. Where are we? Well, we're starting to get configuration reports. We have test reports including coverage. We have generating the build reports, and we can reproduce full source and binaries. So we're now at a point where it's pretty easy to hand this off to people, but we want you to be able to reproduce all our tests. We're going to have a BuildBot instance, and it will be the master will be one of the machines at Oregon State, and the slaves will be wherever they need to be, because like the TSIM license will have to be at OAR. So some of the testing will be remote. If somebody wanted to offer something like a RAD 750 for testing at their facility, they could set a BuildBot slave up for that too. So the future plans, I've mentioned all of those. The target test focus tools are the capture engine, which was recently enhanced as part of the SMP effort. And those take host and target side work. There's always a little bit of work. The capture engine itself has been in RTEMS a long time, but it was heavily reworked for SMP to be lock-free when you're tracing SMP. And there's some work that needs to be done to improve, to define what users really want when it comes to setting up triggers and trace filters. So this is one of those things where RTEMS doesn't, as a project, we listen to users and we try not to invent things, because when we invent things, they mean we implement something you don't want. So we'd rather work with you to get something that works. So hopefully this, the capture engine use, at runtime you have your tasks and they record and put things in the buffers. So the primary things that are captured are done via RTEMS extensions of task switches and task state changes. And these are a combination of those and the generated wrappers. And that data goes through a filter of whether it's on or off. There's some filtering on is the task within the right priority? Are you interested in this task? And then it will go into one of the buffers for the CPUs. The easiest way to make it lockless was to split buffers by CPU. There is an API to access this. This is all working. And right now there's a command line interface where you can display the log. There's also, you can easily retrieve the data yourself, pump it off to a host where there's a listener, and you can decode it into anything you want to. And this is the command line ASCII output for an example of thread affinity on a quad-core system showing the worst case migration. And this is an actual test in the RTEMS source tree. So the first thing that happens is the system comes up and is initialized with 3 idle tasks on the three cores 0 to 2, user task 1 on the core 3, and that pushed the 4th idle core off onto the ready set. The first thing that happens, we created TA1, so you notice that TA1 got switched in. There was a record there. Strangely, they're not in the order in the log. The timestamps are strange if you see it, because things are happening truly in parallel. Creates task 2, kicks another idle task off. Creates task 3, kicks another idle task off. That's not any surprise. So what do we do? Do we create another task that pushed it off? Or do we? Yeah. Okay, so here we raise the priority of task 4, which basically starts forcing other tasks off because of the way the thread affinities are set. So in the other presentation I got today, it's on the SMP, and affinity is really handy, but it also has the property that if you don't do your affinity sets right, This is actually the worst case on a quad-core system. You can actually trickle migrate. You can kick off a low-priority task, which now can only run on another thread core, which kicks off another thread, which in turn kicks off a cascade of affinity. There are rules for avoiding this, but this one's deliberately constructed to do that. And that's the trace on a quad-core system on a test that's actually in RTEMS today. A lot of the SMP work this year, and what the other presentation is on, is the SMP work for the past year. But Aeroflex Geisler, we worked with Aeroflex. This is actually a mock-up of the Gaia flight code that they use to debug things in-house at Aeroflex. It's on a quad core. They took the output of the capture engine, massaged it to get it into the Linux Trace Toolkit. So you can use that to visualize things. We've got a student now who's interested in this. We'd really like to see this come to fruition. We talked to the guys in October at Google about who do the Trace Toolkit so we can integrate, and they're pretty excited about it. And I'm not real good at talking to this because this is actually from Daniel Hellstrom, but the core attributes of this application is that it is a really close mock-up of the Gaia flight code. They're using a multi-threaded API to send messages in the, I can't see that, one of the colors are job threads. Each core has what's called a job thread dedicated to it, and they send a message through the MT API to the job threads. So there is a high priority thread which they schedule activities on jobs into those threads, and then there is background activity which is done by lower priority tasks which can float across the 4 cores. So they have four threads, each pinned to a particular core, so there's no problem with that. And then they have a collection of 12 to 14 other threads that can float among the cores. And this is the timeline of their code. So that's what we should be very close. It can be done by hand now, and we want to automate that so anybody can do it any time using the standard Linux Trace Toolkit. And it's part of, as you open source things and you open community, you want to interact with other communities that have expertise, because I don't want to be responsible for maintaining a GUI. So if I can interface with another community and get a GUI that's well maintained, mature, and has a lot of capabilities, I'd much rather interface with them because they're experts in tracing and visualization. So we can just feed them the data and get everybody a better tool for less work. So the trace linker is what I was talking about that lets you generate trace wrappers and of any type of logging. We've generated them using the capture engine. We've generated them using kernel print. I think Aeroflex wrote them into a different format to generate the other logs that we just saw. So the idea here is that this just needs to be used by users enough to have a feel for how you'd like to use it to help generate wrappers for your application. It's really quite powerful, it's quite portable, and actually it's pretty independent of RTEMS. It's a Python and C++ code that generate the wrappers based on your definition, and so uses anything that uses the GNU tools as the back end should be able to link and use this. So I think I've talked most of this. The future plans for all of the trace visualization is to try to get a portable framework for the mechanism to get the trace to the host. Plan on it being bidirectional. But the key is these are embedded systems where the path from the target to the host is always different. So we have to make sure the framework is actually pretty independent of the communications mechanism and is flexible enough to account for all the various targets everybody has. And thanks to working with people who know more about things than I do, we found out from the Linux Trace Toolkit there actually is a standard called Common Trace Format. And who would have known that if we'd gone out on our own and written our own GUI? So it turns out that if you write things into this Common Trace Format, then all we have to do is work with them on how that's visualized, and if there are certain specific RTEMS events we want in certain colors or triangles or squares or diamonds, then we can feed that into them in some, I think, XML format, and then the events come in a standard logging format. So that's the key to dealing with people who are experts in other domains and leveraging other communities. And that's what we've been really good at. The runtime loader has an API that's based on the POSIX DL Open. It essentially is somewhere in between static and true dynamic linking, like you have on a Linux or a Windows host. Because remember, it's one address space, so you don't need multiple executables to share it. You just want to insert code on the fly and remove it on the fly. So that's what this is done. And it's intended to do as much work on the host system as possible to reduce the load on the target system, because you don't want to download an entire symbol table to the target system if it only has 2 megabytes of RAM, because it won't hold that much. You want your application code, not symbols. It supports compressing the modules. It supports archives. It's basically a nice version of, I think it's wrapped on just standard old libelf. This was recently merged, and it's in the tree today. I think most of the architectures are now in place. There are some of them that are missing a couple of what are called veneers to jump to dynamic addresses, but it's in place for testing and feedback. I think probably most of the architectures you guys care about are probably working. The Spark was obviously the first one we worked on. And GDB has grown Python plugins. So the world's moving to Python. So learning Python has value. And Python plugins to GDB can be very smart. One of the things they can do is display data structures and analyze program variables and things. And so we have a prototype that demonstrates the feasibility of dumping the kernel, some of the kernel structures in a useful to a user mode. We had a student who tried to do this, and then we realized after about half of the Google Summer Code that all they had done was move around code in the prototype we had sent them, and we failed them at midterm. So sometimes you get lucky and sometimes you don't. So we have a prototype and a proof of concept. It really will help GDB know more about RTEMS. I mean, one of the things I've wanted to do is have a GDB plugin that would detect a deadlock and show you the circle of resources, which would be a pain to do on real target hardware. But if you can attach GDB, run a script, you've got all of these known things that are bad, and you can analyze the kernel state and just see what's locked on what and what's waiting on what. So there's some cool things I think you can do. I wrote GDB macros, but they're in a terrible language. The GDB macro language is terrible compared to writing in Python. So this would be a big step up. So this one is on things that most people don't know about RTEMS. These are projects that we've talked about that haven't been far enough along to be either usable or we've begged for help. They're all now starting to come to reality. They're usable. We want user feedback. If there are features missing, we want to add them. We really do want more feedback from the community, because that's why we change things and we add things. MMS, one of the things MMS that's not in this presentation, there's something now called the RTEMS file system, which was written for MMS, and they did the requirements for it, and that's the classic example of how things improve for RTEMS. And once it's in for everybody. So help us by telling us what you want so we don't invent things or go off in a direction that's too random and not useful. So that's...
I'll circulate. Anybody has questions for Joel's?
This is worse than last year.
Yeah.
Let me say something.
Sure.
There are a lot of people in the government community who, like NASA and the civil community, who are, I've told you this before, who want to know how the open source, how to make open source work. OER knows how to do this better than almost anybody. So I would talk to them.
So, yeah, there's a lot of community interaction that's very hard. I've realized looking back that I've done a lot of volunteer work, and the people who in the project, you learn to deal with things. Managing volunteers is very different. Managing community interactions with different projects, how to set requirements, goals, leverage other communities. I'm also on the network time board. Most of the RTEMS core developers are on other communities and participate. Where a lot of us are on open standard efforts. So there's a whole different way of managing your expectations. I guess in some ways, talking to Alan, I hear CFE is fighting some of the same battles of you know, we're having to figure out how to keep this alive without somebody pouring a bucket of cash into our back pocket. So that's what you have to do. I mean, you have to believe in something enough to find a way to make it happen. And you have to have people who want to do it. And so, but we're happy to help people with community issues as you open things and try to interact with other people. because it's really there's some delicate things to have to go through, from checking licensing to make sure people are willing to do things, that politely prodding people to do things, convincing them it's in their best interest. There's a lot of things that go into making a community a success. And occasionally you get somebody who's toxic and you have to deal with them too, which is hard. And that's the unfun side of it, I'll say.
You spoke about test coverage. I think it was statement and also branch coverage. Are there plans to support also MCDC coverage?
Tucker may know more about this. I know in the ADA Corps for the European Space Agency added better branch tracing to ADA to generate the debugging information needed to do the correlation of the traces all the way back to the source language. At the moment, I don't think GCC generates the debugging information for an if statement required to know which conditions go to which particular assembly statements from C. But given we're more than happy to do it if somebody can help us know what needs to be done and help us identify the path to get the information. So our tracing now our coverage information now is done at the assembly level and tracked back to source code. So our assumption is that if it was dead code, something would tell us it was dead code, one of the static analyzers or GCC, and that if it generates code, we need to execute every line of it and every branch path. And I don't know, without having more information from the compiler, I don't know what else we can do. But that's another area where the NASA community and the ESA community really have the world expertise in it, and that's what we want to rely on, because I don't necessarily want to become an expert in MCDC analysis graphs. I just want to know if we're doing it. I was good.
Thank you.